Hello and welcome to iBwave's webinar on Wi-Fi design for stadiums. I apologize for the delay. We had a couple of technical issues. My name is Mary Claire Charlton and I work in marketing and communications here at iBwave. In today's webinar, we're happy to have three fellow iBwavers with us. Nicole Yetzebek, our sales manager for Central and Eastern Europe, will begin with an introduction to the company and the subject matter. Peter Thalmeyer, our Director of Sales Engineering, will then get into some of the key challenges and solutions for managing interference and achieving reliable Wi-Fi network capacity inside stadiums. And finally, Ralph Burkhardt, our Sales Engineer, will be joining us for the question and answer period after the presentation. So a few housekeeping items before we begin. The presentations will take about 30 minutes. And afterwards, we'll be taking questions. So you can type your question in the questions box on the GoToWebinar control panel at any point during the webinar, and we'll try to get to as many as we can during the last few minutes of the session. And for those of you who may have audio difficulties, we will try to speak as loudly and clearly as possible, but please make sure to check your audio settings on your computer or phone as you dial in. Lastly, we'll be recording today's webinar and sending the recording as well as the slide deck to everyone tomorrow via email. And the recording will also be available on the iBwave website by tomorrow. So without further ado, I'll pass the mic to Nicole.
Yeah, many thanks, Marie-Claire, for the introduction. My name is Nicole Yetzebek, and I'm the Regional Sales Manager for Central and Eastern Europe at iBwave. And I would like to go quickly through the agenda for today's webinar, which we hope will be very interesting for you. First, I will say a few words about iBwave and who's using our solutions before I hand over to Peter Thalmeyer, Director Sales Engineering for EMEA. Peter will then provide you with a short product overview before we start with the topic of the webinar, which are challenges for Wi-Fi deployments in stadiums and solutions for Wi-Fi deployments in stadiums. I will then provide you with some further information about our seminar we have planned at the 5th of May in Poland before we go into the Q&A session. As Marie-Claire mentioned, please type your questions in the question box, and the iBwave team tries to answer as much as possible. Peter, next slide.
Yep.
Okay. For those of you who are not familiar with us, I would like to say a few words about iBwave. iBwave is an 11-year-old privately held company with a headquarters in Montreal, Canada. And we are a global provider of innovative in-building wireless software solutions to help operators, system integrators, and equipment manufacturers better design and plan in-building wireless networks inside buildings and venues. More than 700 customers in over 80 countries worldwide trust in our solutions. You can see the logos from some of our customers on the right side of the slide. iBwave is the standard for in-building network design and documentation. You can learn more about our software suite and our in-building trainings on our website, iBwave.com, or get in contact with the iBwave team. And now I will hand over to Peter.
Well, thank you very much for the introduction to the two ladies. My name is Peter, as already mentioned, and what I would like to do is really, for the next 30 minutes or so, guide you through, first of all, our product portfolio, but I promise that only will be very short and sweet and to the point. And then we will talk about our main topic, Wi-Fi in stadiums. So this slide, just briefly, where does iBwave come from? And it's really what we call from the chaos. A while back then, there was no such word as in-building project. It was only special projects that nobody wanted to touch. And back then, many people, when they did an in-building design, be it for Wi-Fi, be it for cellular systems, be it for stadiums, or for normal, if I may say, houses or hotels, people were using Excel spreadsheets to do link budget calculations. They were using very often Visio to do the schematic overview of this design. They were using tools like AutoCAD to overlay the components on a floor plan and all this. And as it is in real life, an in-building project, it always changes. So I need to go back, or I needed to go back then to Excel, Visio, AutoCAD, change it. And this really caused confusion and wrong documentation. So with this in mind, back in 2004, iBwave came up with what we call today iBwave Design. And this is really a design tool for Wi-Fi, for cellular systems, for buildings like stadiums or other complex buildings, but also for smaller buildings. So it's really to go from the chaos to structured data. After we had this design tool on the market for quite a few years and very, very successful, we saw also from our customers that there was a need for a management platform. And this was back in 2010 when we came up with what we today call Unity. And Unity is really a tool that allows you to control your data. It's a management platform, as I already mentioned. First of all, Unity acts like a server. So all the files that are being created will be saved into this server. But on top of that, what Unity does is it drills into this project file and extracts information. And with that, what Unity can do is that I can run queries and reports and get information about this information. So for instance, if I have 300 projects or 400 projects over the last 5 years, and then someone asks me, well, in which of the projects do you have LTE or 3G? Well, I wouldn't know. With Unity, I can run a quick report and have the information at hand. So in 2012, we came up with a mobile version, and this is why we call it iBwave Mobile. And it's really a software tool that runs on either a tablet or a mobile device. And it connects with iBwave Design, and it can exchange information. And the idea is really that instead of printing my design plan on a piece of paper, maybe on A0, and go into the field with a yellow marker, a green marker, and a red marker, I don't do this anymore, but I bring it on my tablet. I go out in the field, and all my documentation that I want to do, and this can be changing the location of antennas, this can be just doing the as-built documentation, and there is a much more that can be done with mobile, and this is really the idea. We stay in the digital format, in the digital domain, and because iBwave Design, Unity, and mobile, they speak the same language, there is no need to convert into PDF, to print and scan. All this not needed anymore, and I can save a lot of time and money. So that brings us to our what we call the iBwave City, where on the left-hand side, and I will focus on the main ones, we have iBwave Design, which is really the design and planning software. At the top, we have iBwave Unity, the in-building management platform, or here it says in-building collaboration platform. And at the bottom, you will see iBwave Mobile, wireless mobility, the tool that runs on mobile devices and really connects nicely with iBwave Design and with and through Unity. On top of that, you might see that on the bottom right-hand side, we have what we call ICP, which is an iBwave certification program. So it's an expert training on our tools. And not only it is a training, but it is also an industry-recognized certification program. So this, as we promised, only shortly about our tools and who we are at iBwave. And now let's jump into our topic. And before we directly jump into that topic, let's get one step back and think about why is it that we're talking about this. And one of the reasons why we do is that the data demand is just exploding. And you see on the bottom left-hand side where we have a little comparison 2013 and where we think, or where analysts think we will be in 2019. So the first one at the bottom, 325 million bring your own device, so that people, they move into an office and rather than having a landline, they use their own device. Then another example, that data traffic, that's the second line from the bottom, it will go from 2.6 exabytes, that's a number with many zeros, but this will increase to 15.9 exabytes. And I could go through this list everything indicates that the data demand is already, and we've seen that in the past few years, and it will also in the future increase. So therefore, we have to make sure that we somehow address this data demand. And Wi-Fi is definitely one of the options that we have in order to address that. And this is why we have that topic today. We also, or in our topic, we have Wi-Fi for stadiums. So let's have a quick look what makes a stadium so special that we hold a webinar about this. So here is just an example, and what we see is, to start with, the 3D structure of a stadium. And by looking at this, a stadium is not, I would say, a normal building where I have maybe one riser going from the very bottom floor to the very top floor. And typically in a normal building, I only have horizontal surfaces, being my ceiling, and walls, so vertical surfaces. But in a stadium, I also have the seating area, which is a bit similar to an inclined surface, basically what we see here. On top of that, in a stadium, we have a playing field. That's also something that's not very typical for a normal building. So all this makes it very, very specific. And even in this stadium, and you might see these yellow lines, I might want to see where is it that my cables are running. I will want to see where is it that I have my antennas and all this information. And here, just as an indication, we show on the seating area with different colors what sort of data throughput we will be able to achieve in this stadium, in this very specific or very special building. And this, in the end, data throughput, that's really the user experience. So we can say that the stadium, and I think it was nicely illustrated by this little video, that the stadium is a very, very special building indeed, and also it is worth talking about. And just for a quick comparison, here what we see, this is the 3D model, and here it is in real life. So that's one thing that makes a stadium so special, but there are other reasons as well that make it so very special. One of them is that we really have a mix of communities with different needs. Well, who is it that goes into a stadium? Well, first of all and foremost, we have the visitors, and this is the big crowd. And what are they doing? Well, they're taking pictures. They want to even upload pictures to Facebook or whatever and say, wow, look at this, here I am, and this is the concert, or this is the soccer or football game. So they want to use data. If it's a football game, they maybe even want to see how other teams are doing to compare it, so they want to download this information. Another crowd, I would say, that we have in a stadium is the operations team of the stadiums. So these are typically the people who show us our way and help us with things. And also they need communication systems and they need data online. So another reason, and not necessarily the visitors and the stadium operations have the same requirements, so we have to plan differently for that. On top of that, what we can have in a stadium is the event personnel. So just imagine if there is a rock concert in a stadium, then the organizer of the rock concert will bring his own people into this stadium. And again, these guys, they need to communicate, they need to have data available, and so on and so on. And then on top of that, we have the press, we have the security people. So that really shows us it's not just someone who goes into a stadium. No, there is different people, different communities, and they have different needs. If we look at the radio challenges in a stadium, again, I would say it's pretty mixed. First of all, we have a mix of play fields. So today, it might be a soccer or a football game, and these guys on the football ground, they don't need much data. They have to run, they have to, well, get the ball into the goal, but they don't use much communication. The referee maybe does. Now just imagine within 2 days that changes and we have again a concert. So all of a sudden, where the playground was yesterday, now I have a huge crowd who want to use data. And this makes a big difference for my radio challenges that I have. Then in a stadium, well, I have concession areas, I have the seating areas, they have different RF performance. I need to look into this. The seating area, I can maybe model it as an inclined surface. But also what I have in a stadium is that behind the scenes, if I may say so, in the basement, for instance, there might be the changing room for the top players. There might be press areas. So all this, completely different scenarios. It's not just one building, it's one stadium. Yes, it is one stadium, but there are different requirements. Then if we move on to the capacity demand that we have in a stadium, first of all, it's very peaky, because if the star comes to the stage, well, everybody wants to take pictures and upload them onto the internet, or if it's a football game, everybody wants to film the goals and say, hey, wow, I've seen it live. So it's a very peaky demand. And on top of that, if you look at the density of people in a stadium, I would say there is not much that can make it up to that. So I really have a high densely populated area, and they want to have a lot of demand. We also have a mix of systems. So we have, for instance, Wi-Fi, we have cellular, we have other stuff in there. So also this makes it special. And last but not least, sometimes we techie guys, or me as a techie guy, I forget the business aspect, because the stadium sometimes cannot even open if the cellular system is in there because of security reasons or whatsoever. So all these things, we have to keep them in mind. Now, we have seen why stadiums are so special. We have seen the different requirements. Now let's have a look at our Wi-Fi challenges. And you will see that we have split the challenges into coverage, then we will move on to capacity, and then interference. But for coverage, in order to get seamless coverage, you need to have what I call overlapping cells. And what I mean by that, if we look at these circles, and I'm just assuming that the circle is, let's say, the coverage range, then you need to make sure that these circles have an overlap. Because if you have a gap in between, and if you want to do, for instance, voice over Wi-Fi, you will not be able to have continuous voice. For voice over Wi-Fi, you might even have a larger overlap to avoid technical constraints. So that's something we really need to look into. Also, if we look at the coverage for data throughput, and we do sectorization, again, if we look at these circles, I should make sure that, and you will recognize this by the different colors, that I have different channels next to each other. Why? Because the same channel would cause interference. So also this is something I would need to take care of. And typically in Wi-Fi at 2.4 gigs, we talk about in our regions for the channels 1, 6, and 11, because they do not interfere with each other. And we will see another slide about this. So again, the access points of the same channel number need to be properly separated. And this is indicated again here by the different colors, where I have black, green, red. Also here I have green, red, black, so that green and green never touch each other, and black never touch each other. And also one challenge that we have is that we have a huge area that needs to be covered, whereas we have typically pretty low output powers coming out of an access point. It's typically in the range of 20 dBm, depending on the regulations and depending on other things. So with that in mind, let's move on to the next challenge, which is capacity. And if we talk about capacity, I have to ask the question, how many access points do I need for a given number of users? Or maybe in other words, how many users can I cover with one access point? And that, how many do I need for the complete stadium? Well, also one important aspect is, what do users expect? So what is their usage behavior? Are they just looking at their emails every 30 minutes? Or do they want to download and look at videos and things like that? So that really changes these calculations that we have to perform here. So I'm just going through an example, and it's just a example where we say, let's assume we have 500 kilobits per second per user. This is what the user eats in bandwidth, if you will. So this is what he requires to have proper video streaming and so on. Let's say we're using 802.11g, and again, this is just an example, and we're aiming for a 10 megabits per second cell edge or coverage edge, and this depends on signal-to-noise and interference ratio, but let's just assume we can achieve that for now. And now let's assume that 25% of our users have Wi-Fi enabled devices. And let's also assume that 25% of the users are using it at a time, because most likely not everybody is using his device all the time. So these are just assumptions. So with that in mind, we have 10 megabits per second. This is what one access point can give us. We know that we have 500 kilobits per device or per user. So I can divide my 10 megabits per second divided by 500 kilobits per second. This, in turn, I can divide by 25% because this is the Wi-Fi enabled devices that I have. And I can divide it again by my 25%, that's the usage that we have. And with that, we end up with roughly 320 users. So that means one access point every 320 users. And now just imagine, what sort of footprint would that be in a stadium? So that already gives us a good picture how many access points we need. Because these stadiums, well, they range from, I don't know, very low numbers, hundreds and thousands, but there are also stadiums out there with 70,000 and even 100,000 seaters. So that gives me an indication as to how I have to dimension and what are the challenges that I'm facing with all of this. So I promised that I will show you a slide with the typical 1.6.11 structure, and this is what we see here. At the bottom you see the different frequencies, and here in blue you will see first of all channel 1, the center frequency being 2.412 gigahertz. Then here we see channel 6 indicated here, and then we see another one in blue, channel 11. And what I see here is that these three channels, they do not interfere with each other, or what I mean by that is that they don't have overlapping frequencies. Because if I have overlapping frequencies, it would mean that some of the energy is disturbing the other channel over here. You will also see that we have such a repeated pattern. Let's say if we take the red curve over here, this would be channel 5. Then we would have here channel 10. And depending on the region, in our region this is not available, but it would be channel 14. And also these would give me a scenario where my channels do not overlap with each other, and therefore I don't generate interference, more or less. But you see also there are other channels in there, the green one for instance, channel number 2. And that shows me already, if I were to use channel 1 in blue and channel 2 in green, that there will be a huge area where we have the same spectrum, the same frequency, and this would create interference. So I really have to do a proper channel planning. And when we talk about interference in Wi-Fi, and well, it's almost for everything, but on the 2.4 gigahertz band, we have to look into adjacent cell interference, and this is what I just mentioned, that channel 1 and channel 2, they have a lot of common frequency band, and therefore they will interfere with each other. But we also have, and this is what we see the second bullet in red, we have co-channel interference. Some call it co-channel cooperation, which is basically that if I have channel 1 and channel 1 again, that will be full interference. And this is something I want to avoid, and this is what we have seen in one of the images with the different circled colors, where we had black, red, and green, and where we want to separate that. And one thing we must not forget when we talk about Wi-Fi, it's an unlicensed spectrum. That means almost everybody can do almost everything. Of course, there are, even for this band, regulations. But if someone decides to create a Bluetooth headset and use it, if someone decides to use his microwave oven, which is very, very close to this spectrum, if someone decides to use a DECT phone in this frequency, so basically a wireless landline phone, if I may say so, everybody can do that in this frequency band. So that means I will have interference from other devices. And I cannot control or avoid them. So I have to plan for them. And this already brings me to my next slide. How can we address this interference? And you will see that for the challenges I talked about coverage, capacity, interference. Now let me inverse that, and when we talk about the solutions, let me talk about interference first. And what I see here on this slide, let me just explain. You will see all these tiny little dots on a floor plan. And these dots, they come from a survey that was done on this floor plan. And you will see up here the legend that shows you NEC 100, for instance, would be black, and pink illustrates NEC 40 dBm, and this is just RSSI for now. And what I see in the complete colored thing then is an interpolation of this walk test to my whole floor plan. And why do I say all of this, and what does that help me? Well, this one here, we will see it was done for channel 1. So someone did a survey on this floor plan, and now I'm just filtering what I see on channel number 1, and I see that in this area I have a very, very high level, but in this area it's lower, but it's almost the same as in this area here at the top left-hand side. If I move to the picture on the right-hand side, though, you will see that this is channel 11. So we're back to famous 1611. So it's just another channel. And to illustrate, for this channel, I have way less power on this floor already. And in this corner, it's extremely low. So if I had to make a decision for this floor, if I want to plan a system on channel 1 or 11, I would see right away that I would pick 11, even though in some of the areas I still have high interference, but it would be way, 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 way lower than what I have here on channel 1. This was an illustration with different channels, and a similar thing here with different SSIDs. And an SSID is more or less the name of the Wi-Fi system. So what we see here is, here this is named guest Wi-Fi, and I see that guest Wi-Fi, the access point is probably somewhere here or there, and it quote-unquote covers this area, whereas this area over here is not covered. And it might be that I know this SSID and I know that it will be switched off. Or here is another example. This is a different SSID that has a completely different RF behavior. And again, this is information. If I know my interference, I can handle it. And this is really the message we want to get across here. I need to be able to handle my interference. So if I move on then, now let's look at the solutions. And now I don't even distinguish anymore between coverage and capacity. They somehow go hand in hand. But let me just explain how we tackle the solution. Here on this slide, on the very left-hand side, we see what we call the design plan, where we really nicely structure the components that we have. And here, for instance, you see an access point, and you might see, or you might recognize the colors again, red, green, black. So different channels, 1611. And here, just to demonstrate how we structure them and how we connect them to a router or a switch or anything, just to create nicely my overview, my systematic overview. From left, let's jump to the right, where we now see in a seating area of a stadium, and of course this is a small stadium, and some of you will say, well, the number of access points is never sufficient for this seating area, and I would agree, but to demonstrate how that works, you will see here the different access points, and you might see the calculation that's shown here in green, black, red, which means they are different channels. And what I see here on this one is really the signal strength. So I see the best serving signal strength from all these access points. And here in the middle, in the center, I now see the best server. I see which access point, this one for instance here, covers this blue area. This access point here covers the red area. and so on and so on. And this is really something that I want to see, a nice separation between them. And of course there is some overlap in signal strength, but here it is more important to see the structure, which access point is covering which area, and this is what we just call best server map. Now I've talked about access points. What do I need to know about these access points? Well, what is important is, first of all, which band I'm working in. Is it the 2.4 gigahertz band? Is it the 5 gigahertz? And there are some other bands or frequency bands planned. Then, what is also important, I need to know which technology I'm working in. Is it 802.11bg as indicated here? Is it 802.11n, or is it 802.11ac, which is one of the later standards? And also important, the channel. And here we see again our 1, and if I would scroll down here, 6, 11. So this already allows me to define my access point if I use it. And what is also important when I talk about the access point is that maybe I already want to use a certain model from a certain manufacturer, and what is for sure important is the output power. And here, for instance, we see that 20 dBm. And then, of course, it depends whether the access point already has an integrated antenna or I need an external antenna. So just things like that. And if I plan my system then with these access points, knowing which frequency, knowing which technology, knowing which channel, knowing which output power, knowing which antenna, then I can go back and do my coverage. This is again an example that we see here. Signal strength, that's basically the coverage. And here on this one, we also have a legend that shows us again which color corresponds to which signal level. And for the same area, what I see here is again my best server map. So this is just before it was a seating area. This is now aside the stadium in the concession area. But again, I want to see which access point covers which area, because one of the things I also want to know that the number of people that are covered by this access point is sufficient, or let's say the access point is sufficient for the number of people that I have. And what is also key is SNIR. SNIR stands for signal to noise and interference ratio. And the SNIR is really what drives my data throughput, because data throughput depends very much on the SNIR. And again, we see in different colors what sort of SNIR values we have, green being very good. And you see here in this area where I have several access points contributing, now they're interfering with each other, and therefore my SNIR drops down to blue or yellow or some spots even red. SNIR is something for us engineers, but for the end user, what he wants to see is what we see here in the center, and this is the data throughput. We call it max achievable data rate map. So here on this one I see green. Everything that's green on this one, I have 135 megabits per second, and I see where I had bad or not so good SNIR previously, I do have lower data throughput. And here on the left-hand side we have soft handoff map, which is not really a term that we use in Wi-Fi, but again it shows me where the access points are dominant and where they are not. And a very similar map that we call the service count map shows me how many contributing access points do I have in a region. So here, for instance, in black, it tells me it's only one access point that's really providing energy, whereas here in dark blue I have 2, light blue I have 3, and so on and so on. So also a criteria that helps me to look at my design and say, yes, I did it properly, or, ooh, maybe there is room for improvement for me. One thing that is key, and we did our calculation in the beginning where we said, okay, I need a certain amount of access points for the amount of people that I have, or the other way around. But when we did that calculation, we were assuming a few things. And one of the things that we were assuming is the cell edge data throughput, or let's say the average data throughput that I can achieve with an access point. In our example, it was the 10 megabits per second. But when you think about all of this and all the maps that we just looked at, this 10 megabits per second very much depends on the signal to noise and interference ratio that I have with the design. So also my calculation, or let's say the result of this calculation that we did, is dependent on the real-life RF scenario that I will be able to achieve. So what we see here on this one is where I take all of this into calculation, and now I do a different approach. Now I know I have put so many access points into my design. I know that one access point, well, if we neglect the backhaul for now, but then I know that the access point can do a certain data throughput for a certain area. And now what I have done here with this report is that I said, okay, now tell me, under the real RF performance that I have with my design, knowing the real number of access points I have my design, and now I can run this report and tell me how many people can I support with this design. So this really closes the loop between my planning that I did in the beginning, and now I get the confirmation through this very report. So I hope that this illustration, where we looked into the challenges broken down into, well, stadium, why is it so special? But then we looked into coverage issues, we looked into capacity issues, we looked into interference issues, and then we looked at the solutions and how can we go about all these challenges, how can we fix it and still come up with a good design, where we started now with the interference, then looking into coverage and capacity. I hope that it was helpful, because for me, for my part of this presentation, the technical part, I'm done with this now. And now I would like to hand over to Nicole again, who will mention a few things about the upcoming seminar that we will have shortly in Poland.
All right, thank you very much, Peter. Yeah, as I mentioned in the beginning, we would like to invite you to our seminar with the topic Wi-Fi Design for Large and Complex Venues. iBwave will held at the 5th of May in Warsaw in the Canadian Embassy. We have invited very interesting guest speakers who will share their experience with you and join a very interesting panel discussions. And the invitation for the seminar in Poland will go out shortly. And now we'll hand over to Marie-Claire, who will start with the Q&A session to answer your questions.
Thank you, Nicole, and thank you, Peter, for the presentation. So we're now going to start the question and answer period. You can type your question, if you have one, in the questions box on the GoToWebinar control panel, and we'll try to get to as many as we can within the next few minutes. So we'll begin with the first question. How can I include measurements of existing RF signal on inclined areas for SNIR calculation? Peter.
Okay, well, that's a good question. Basically, out there, and if we look at Wi-Fi only, also we at iBwave, we do have a tool that allows us to do walk tests. And with these walk tests, we can measure the RSSI from different SSIDs, and we can then, after that, filter it according to the channels and the SSIDs and so on. And we can do this on the inclined surface, on the seating area, and because this is what I just described is mobile, it has the same language as design, I can simply bring the file into iBwave Design, and then I can do SNIR measurements. If it is for, let's say, not Wi-Fi related things that I cannot control, which I would say is the minority, but here I would need to do a quick check with the spectrum analyzer, and also this is something I could address in iBwave Design. And for those of you, if I don't answer your question to your full satisfaction, please forgive me, but you will see our contact details and you will have them. So if you are keen on discussing these topics further, we can always take it offline and we can show you how this can be done. And I hope that answers the question. I give back to you, Marie-Claire.
Okay. Thank you, Peter. I have here questions for Ralph Burkhardt, our sales engineer, who's on the line. Antenna type and placement are critical in crowded areas like stadiums. How can iBwave support identifying proper antenna selection and placement?
Many thanks, Marie-Claire. Let me answer this question. Stadiums are challenging venues for which special radio design techniques are required. With the help of a 3D model and a 3D viewer, which we have in iBwave, you can easily identify the antenna positions, which do not obstruct fans' views, and on the other side, provide sufficient coverage and capacity to your network. In addition, venues like stadiums have aesthetic guidelines that must be maintained. So, if the antennas are not well integrated in the appearance of the venue, they will not be tolerated. iBwave's online component database is updated regularly with the latest list of components of equipment vendors, which will help you selecting the proper equipment and antennas for your venue. So I hope that answers the question, and I would like to hand over back to Marie-Claire.
Thanks, Ralph. So another question for Peter here. How does the tool treat 3x3 or 4x4 MIMO, and how is MIMO considered in the capacity calculation?
Oh wow, that's already a pretty detailed one. So at the moment in the tool we treat 2x2 MIMO because we see that many devices, especially the mobile devices, they're not 4x4 yet, but of course this will change over time. But this is one of the reasons why we focus on 2x2 MIMO today. For 2x2 MIMO, be it Wi-Fi or cellular space, you can deploy your whole network with the 2x2 MIMO. And then what we do for data throughput calculations, we apply a certain factor depending, again, on the SNIR, because the SNIR is always something that we know. And from literature, and also, I would say even more from customer experience, they have seen that for certain SNIR values, they can assume a certain MIMO gain. And this is what we put into our tools. And with that, we can do the calculations for data throughput.
Thank you, Peter. I have here another question for you. Can you please explain why you used 10 Mbps as a baseline for your capacity calculation?
Oh, okay. Well, it is a bit like what we just said now, but yeah, the 10 megabits per second that I was using for my calculation was just an assumption. Because I know for 802.11bg, I can reach way more than 10 megabits per second. I can reach 54 or whatever, depending on the technology. But this 54 megabits per second is something I only have very close to the access point, because very close to the access point, I have a very good SNIR. As I go further away from the access point, my SNIR goes down because my signal goes down, and my noise floor, at least the noise floor stays the same, so my SNIR gets degraded, and with that also my data throughput gets degraded. So I cannot really assume that everybody will be served at 54 megabits per second, so therefore I took a conservative assumption and said, okay, let's calculate with 10 megabits per second. And of course, it is an assumption, but we need to start somehow, and this is why I used the 10 megabits.
Perfect, thank you. I have a question here for Ralph. Do we have a sample Wi-Fi stadium design, and is there any way to access this?
Yes, Marie-Claire. We do have sample Wi-Fi stadium designs available, and you can either start a trial with our iBwave design to get access to the Wi-Fi stadium samples, or you can join our session in May, which is about Wi-Fi for stadiums as well.
Perfect, thank you.
Thanks.
Peter, do you foresee project synergies for Wi-Fi and cellular indoor system implementations in the case of stadiums?
Well, I wouldn't even limit myself to stadiums, but the answer is a clear yes. And especially if we look at stadiums, because some people or some customers, they ask me, well, a 3D model, and I say, well, would I do a 3D model for each and every building? For a stadium, yes, definitely I would. Because if you want to do things in a stadium, just one example, you put an antenna on the gantry, and then you do walk tests. To get this antenna up there, it will take security clearance, you need a crane that gets it there, and so on and so on. So it will cost you a lot of money and a lot of time to do that. Then you can do your walk test, but then you realize, maybe I want to change the tilt of the antenna or the alignment. So you need to go again through security clearance, you need to get the crane, and again you need a lot of money and time. So it would be much, much easier to invest that time, and it's a fraction of that time, to do the 3D model of the stadium, and then with a few clicks you can simulate what happens if you change the tilt or the direction of the antenna. And now getting back to the real question, do I see synergies? Oh yes, absolutely, because once you have created your model, once you have collected your information on site, why should you limit yourself to use this information only for Wi-Fi or only for cellular? It's there and you can use it. And if you did it once, you will use it again and again. And if tomorrow there is 5G and in 10 years down the road there is 6G or whatever, I will still reuse that information. So there is a huge synergy effect.
Okay, thank you. Another question for you, Peter, and I hope it's not too detailed, but can we calculate the number of users that can be served by an average data throughput? And if so, how is it calculated?
The answer is yes. It is a bit detailed, and but we probably can take that offline as well. But in short, I can put the access point somewhere. I can run my predictions, as we call it. I do the SNIR. I will have a mapping depending on the technology. A certain SNIR will contribute to a certain data throughput on several areas. Then I will use a completely statistical model, populate my users in that area, so they will then know what sort of data throughput they get. I will assign a usage profile to the users. I will define a blockage percentage, and with that the tool will tell me how many users I can support. I know that was a very crisp answer, which is probably not explanatory enough, but again, please feel free to contact us and we can take that offline and we can jump into the details.
Okay, thanks. Another question about iBwave design for Wi-Fi. Does it calculate adjacent channel interference?
The answer is no, yes, no, because not today. Yes, in the upcoming release we will.
Right, okay. So you're talking about the release that's coming up in about a month.
Yeah, exactly. I think it's planned for April. Mm-hmm. Yeah, sorry.
Okay.
I should have mentioned that. Thanks.
Perfect. So as we had planned this webinar to be 50 minutes, we are out of time now. So I'd like to thank everyone who joined us today. If you posted a question that we didn't answer during the Q&A, as Peter mentioned, we'll make sure to respond to it via email within the next few days. And feel free to contact our speakers if any additional questions come to you. You can also communicate with us at any time via Twitter, Facebook, or on our iBwave user group on LinkedIn, which is a great place to keep this conversation going. You can look for a recording and the slide deck from today's presentation in your inbox, and we'll also be including a registration link for our upcoming seminar in Poland. So I hope you'll be able to join us there and meet us in person. Thanks again to our presenters and panelists, and thanks to all for taking the time to join us today. Have a great day, and I will now disconnect the call.
Thanks, everybody. Bye.